My name is Junho, and I'm a PhD candidate in Industrial and System Engineering department. And as you see in here, my specialty is human factors and ergonomics. So I brought the topic with a guideline for cognitive workload classification. Actually, this study is a small kind of a literature review study. So unlike previous slides, it might be a little bit boring to you. And then I was not able to prepare that many figures or some good visualizations, but I hope that you do not leave this meeting. Yeah. Yeah, there are 4 chapters. Yeah, if I start from the beginning for you, cognitive workload. So we simply talked about it. It is kind of mental stress, and then this is a used amount of working memory resources. So it's heavily related to HCI, human-computer interaction, and human-machine interaction. For example, driving or some healthcare situation. So there's a way to measure this cognitive workload. So the major one is the physiological data, like a heart rate or skin conductance level, as you see in the figure on the right bottom. And then there's also a way to measure it with the survey questionnaires. So after some kind of experiment, we can ask participants to answer their level of stress on the paper. And then task performance is also the measure to measure the cognitive workload, their performance in the middle of their interaction. And the last one is kind of the computer modeling technology. However, there's some issues. Those physiological metrics, as you see in the figure on the right side, you can also feel that there's a high intrusiveness, which means that in the middle of the interaction, human usually they need to move their hand or their body, and then although the technology has been improved a lot, there's a kind of too much noises in the data, the low data, and then that will also make the data analysis, which is really become much more difficult. So, and also second one is the participant recruitment. Considering the COVID-19 situation or some studies with physically disabled people or cognitively impaired, for example, older others. These days, it's very hard to bring them into the laboratory, and then putting those kind of annoying sensors on their body is really kind of challenge, and also cost in this time, and then also money and also manpower. So from listening, there are a huge number of studies that use the machine learning or deep learning technology to predict the cognitive workload with minimal kind of optimal subset of the data. So the study of this is simply speaking, machine learning is a study of computer algorithms that can improve automatically through experience and by the use of the data. So there's also controversy between with the topic that what is the difference between the kind of inferential traditional statistics and the machine learning, and then I put that as a table in the appendix. So if you want to see that kind of difference, I can also show it to you. However, in this presentation, I will use the machine learning and deep learning. So I did small kind of a scoping review with these keywords and database, and this is a screening procedure. Then I finally got the 23 papers that classified cognitive workload. So some of which papers made. So from this slide, you may not be familiar with this kind of abbreviations. So I prepared the abbreviations on the left bottom. So each abbreviation in this pie chart is kind of a machine learning and deep learning techniques. So SVM, for example, there's a support vector machine. This is kind of one kind of methodology to classify cognitive workload. So each abbreviation means some different algorithm. So there are a bunch of algorithms in very diverse domains. For example, in the medical domain or the surface transportation domain which are very general, a healthcare domain, or some construction domain, a military domain. They use, however, their common purpose is to classify the cognitive workload, and then they used this technique. So recommendation is that the major techniques are the support vector machine and random forest RF, and the naive base. And then this is not only these three are not just the major algorithms for the cognitive workload, but also they are very highly used in just in the normal cases of the machine learning or deep learning. And then this graph shows that there's no significant relationship between the x and y axis. The x axis is the number of feature types. So 2 means that these studies combined 2 x variables, for example, physiological, so human heart rate, and then task performance. 3 means that these 3 studies combined 3 x variables. And then y-axis means that the classification accuracy, which is the major metric to determine the algorithm's performance, the classification performance. So accuracy is a really important metrics that we need to look into when we talked about the machine learning and deep learning. Many studies use many types of studies. However, if you see the R-scale value here, although there's so many studies use only one feature, and then their accuracy shows still very high. And then type of features, type of X variable here, more than 60% of the studies, these studies use heart rate and eye tracking and a skin conductance level to measure the participants' stress level. And then a small number of studies use the EMG signal, the electric signal from the muscle movement. And then also they use kind of a survey metrics. So a recommendation for the type of number of features based on this graph is that, so this red dot bar is kind of a threshold to determine the performance of the algorithm. Here, test performance and combination of some of these 2, and then EOG, so eye tracking and the pupil related measure, and then the ECG or heart rate related, those kind of measures can be appropriate for to measure the cognitive workload. So I brought 3 discussion points. That first one is that the trade between the demand of the experiment and the research should be addressed. As I said, that human subject experiment involved huge costs and risks. So we need to consider the merits of having multiple input signals instead of having 1 or 2 signals. And the second one is that we need to do the modeling features as inputs. So still, currently, majority of studies relied on the physiological signal and the CPM. So cognitive performance modeling. Computer software can be a candidate to replace those traditional features. So because CPM is very close to the task performance, and then there are tons of studies that show that modeling outcome can be very similar with this physiological data, the pattern of those data. So CPM can be a good kind of substitute, and then this can hugely reduce the experimental cost, and then improve the versatility of the research. However, the developing that CPM also requires the expertise and also time and programming skills. The last one is that regarding the machine learning, deep learning, many studies did not clearly stated that the detail of the machine learning process or some major steps they need to do to reach to the optimized model. So this is the last slide. So as a procedure, I recommend following these steps from feature extraction to cross-validation, and then the number of feature types as small as possible, The type of feature is also including the CPM to minimize kind of intersimilarness with that physical interaction. And then the machine learning algorithm based on the two algorithms based on the input data size, the cross validation, the number of K-fold size in here. This is all of my presentation. Thank you.